Hello, CCP1 students. This is Dr. K. As promised, I was giving you a video key for your sample test for Chapter 6. So if you have any questions about how to do different problems and stuff, you're not left to surprise and stuff. So I'm going to go right to the test that you're doing as a practice. All right. Okay. Conceptual questions. Yeah, those are some things you have to study a little bit more and go through your notes, go through the PowerPoint, maybe the book, and think about some of the things you learned. Sometimes they have to do with the equations you do, but what the outcomes are and what the patterns are and stuff. But pay some close attention to them. Given that we don't usually have quizzes on them, the quizzes seem to center on the application problems. Okay, so the first one, all moving objects, regardless of mass, have a de Broglie wavelength. That is correct, they do. Even you have a wavelength, you just can't see it. All moving objects have a wavelength. Electrons being as small as they are, light, all moving objects. And there is an equation you're supposed to know and use on this exam. We never had it on the quiz though, so that's kind of a heads up on that. Wavelength is directly proportional to energy for light waves. You're like, I don't know. Well, let's figure it out. What are the equations you're supposed to know? You're supposed to know that energy is directly proportional to frequency. Okay, so that doesn't answer anything. We're looking at wavelength. What do we know about wavelength? Wavelength times frequency equals the speed of light. The speed of light is always constant. So in other words, your wavelength is actually inversely proportional to your frequency. The bigger it is, the smaller this has to be. So if that's true, if wavelength and frequency are opposite of each other, and frequency and energy are not opposite of each other, by inference, wavelength and energy must be opposite of each other. So this is false. So that's just knowing your equations. Here's some true and false. They have to do with your quantum numbers that are very important. But you all did very well on this on quiz 2. First quantum number, that's n, principal quantum number. That is true. Main thing was, is it the right symbol? We also talked about filling electrons. We called it Hund's rule. You single fill everything in a single subshell before double filling. That is true. The other ones to know are Aufbau says you fill in the lowest energy subshell before the next energy level. And Pauli exclusion means don't put two up arrows in the same orbit. Energy of a photon of light is inversely proportional to frequency. We just showed that that's not true. That's actually directly proportional. So put a false there. There are 7 p orbitals. Well, p is quantum level, second quantum number 1. So your m sub l must be -1, 0, and +1. And you've been putting in p6 a lot. If it was 7, you would be putting in p14. 7 actually refers to your f orbital, so we'll put a false there. All quantum levels or shells have a p subshell. Okay, if you're quantum level 1, what can your L be? 0. What is 0? S. Can you have a 1 or a p subshell in a 1? No. So basically, this is false because the first quantum level cannot have a p subshell. It's only the second one that has it. The brightness of a light is directly proportional to the energy. That's actually false. It's actually proportional to the frequency. So we'll put a false there. That was the surprising thing about light. Okay, Pauli exclusion principle states that electrons fill the lowest energy subshells first. No, that means you make sure you have an up and a down arrow, so that's false. What's described there is actually Aufbau. And this one we didn't do, so we're going to cross that one out. Next one, kind of what you did in lab, what you did in the first quiz. We're looking for wavelength. Wavelength equals c over frequency. But we don't know what the frequency is. So let's go to the energy one. Energy equals h times v. Okay. So how are we going to find v to get wavelength? So we know this. We got it up there. So what we'll do is we'll put E over h. We'll solve for that and get our frequency and plug it into here. You can do all the algebra one or whatever, but let's try it a little bit. So 6.34 times 10 to the negative 19 joules divided by Planck's constant, which is 6.63 times 10 to the negative 34th joules times seconds. Okay, I'm going to just guesstimate this as to being pretty close to 1. I'll put it as 0.92 times 10 to the 15th, which is another way of putting it as 9.2 times 10 to the 14th per second. Seconds to the minus 1. So now I can put my speed of light, 3.0 times 10 to the 8th meters per second. Where did I get that? It's up here. I'll divide that by my frequency, which is 9.2 times 10 to the 14th per second. These cancel out. And I get about 0.3-ish times 10 to the 6th, otherwise known as 3 times 10 to the 5th. I'm sorry, that's 10 to the negative 6, my bad, to the negative 7th meters. You don't, in this one it doesn't say you have to convert it to nanometers. Okay, Rydberg equation. Notice we're given it. Where's the Rydberg equation? It is right here. You do have to interpret the ends though. This one I call it initial and what it falls from. So I call it F for where it falls from. So anyway, let's put it in. So yeah, fun. 1 over wavelength, which will come out in meters, by the way, equals the Rydberg constant. Let's look up that again. 1.1 times 10 to the 7th meters to the minus 1. Then we're going to go 1 over 9, that's 3 squared, minus 1 over 16. Okay, so you can organize it after that, but it's pretty easy to do it. Using the Rydberg wavelength in nanometers. So after you get this one though, how do you go from meters to nanometers? You're gonna, when you use the Rydberg, you get your wavelength in meters. What you do is you basically multiply it by, there's 10 to the 9th nanometers per meter. Okay, so you need to make the number bigger because you're going to a smaller unit. Okay, how much energy is released in question number 12? Okay, very good. So if you have the wavelength in nanometers, well, you actually also have the wavelength in meters. What you can do is this. So a lot of rigmarole here, but energy equals h times frequency. But you don't have frequency, but you could put c over your wavelength equals frequency. But just remember, when you put 3.0 times 10 to the 8th meters per second, you better put in your wavelength in meters, which you probably got originally in the last one. And then once you get that, you can plug that into here and multiply it by Planck's constant. Okay, what about de Broglia's wavelength? What is the equation for that? Let me see. Did I give it to you? I probably didn't. Let's see here. Okay. Let me make sure I have that one with me. So you have to memorize it for the test, obviously, because I don't have it here. Let's see here. Okay, de Broglie wavelength. So this is a good thing to say, hey, we got to do this. De Broglie wavelength, by the way, equals Planck's constant over mass in kilograms times velocity. This mass better be in kilograms, and this velocity better be in meters per second. Or else. Let's look up Planck's constant again. So Planck's constant is actually the same units, but here we go. But to make it jive with what we're putting in, we need to put it into kilograms, meters squared per seconds. Okay, so what we do then is we put in 6.63 kilograms, meters squared per second. And we put that over how many kilograms we have. Wow, not many. So how do we get grams into kilograms? So this is telling you have to do this, by the way. 5 times 10 to the 24th grams. Well, it turns out you have 1 kilogram per 10 to the 3rd grams. So you're going to end up getting 5.2 times 10 to the minus 27th kilograms. I know, kind of ucky. Here's your kilograms. And then your, oh, wonderful. I wasn't very nice on this problem. Okay, so now we have to get this into meters per second. So that it cancels out with some of the meters per second there. So 3 times 10 to the 7th miles per hour times, I know there's 1.61 kilometers per mile. So that's going to come out to be somewhere around, I don't have it perfectly in my head, but I think it's going to come out to be almost 4.9-ish times 10 to the 7th kilometers per hour. Then I have to multiply that by 10 to the 3rd, so I'll get 4.9 times 10 to the 10th meters per hour. And then, after I get that, I'll have to convert that and say, let me put that up here, 4.9 times 10 to the 10th meters per hour. Now I'm going to have to multiply that by, I have 1 hour per 60 minutes, or let me just put this way, per 3,600 seconds. So I'm going to divide that by 3,600, and finally I'll be able to put in a number here. When I finally put in a number here, do you guys notice that meters, now I have just meter up here, my seconds cancel out. I will get my wavelength in meters, and it doesn't say I have to put it in any particular unit, I can leave it in meters. But notice I had to do some contortions. My velocity has to be in meters per second, not kilometers per hour or miles per hour. And I also have to put my weight in kilograms. So there's some things to make sure you work through on 14 to be able to do de Broglie. Okay, we've done this in quiz 2. Let's look for numbers 1 and 2. Those are good, those are good. I'm probably preaching to the choir here. I didn't make any of them bad as far as the first 2 numbers. Let's look at the second 2 numbers. We're good. Not good. You have to be between 0 and 0, so this one's not good. This one's good. You can be -2 if you're 2. This one not good. This one good. And the last one not good. You can't be a 1 if you're a 0 there. Okay, so what subshells are in quantum 3? It's kind of like saying what can L be? L is always less than or equal to n-1. That means L can be 2, 1, or 0. Well, what is 2, 1, or 0? 2 equals D, 1 equals P, and 0 equals S. There we go. How many orbitals are present in an F shell? Well, what is F? F is 3. What are the orbitals? -3, -2, -1, 0, 1, 2, and 3. So those are your numbers. Which quantum levels or shells have F shells? Wow. Well, if your L is 3, and L is less than or equal to n, less than or equal to n-1, you're going to get that n has to be at least 4. So we're going to put 4 here and up. Okay, so M sub L, magnetic spin number, is -3. Which subshells could be in? Implying it could be more than 1. Well, that means L has to be 3 or up. Why? Because M sub L is from positive to negative of that number. If it was 2, -3 wouldn't be in there. So L has to be 3 or 4. Well, again, L, 0 is S, 1 is P, 2 is D, so this is at least F. That's only one we have to list. Even though there's a G and an H, we don't use them. Which shells contain F orbitals and which do not? What am I doing? Which shells contain them? I just did that one. Oh, I'm sorry. We said it could be an F subshell. Now we're asking what shell could that be in? And I just did that. I did that in 17B, so whatever. Give the electron configuration. Okay, PB is actually, it is a 6p2 guy. 6p2. I gotta write everything out. I stare at the periodic table and I look at row 1. I look at row 2. I look at row 3, which is the same as row 2 with different quantum numbers. Row 4 and 5 are SDP rows, with the D being one less. Then row 5, same as row 4. Here's row 6, it has an S block. An F block, sorry, not an S block. It does have an S block, of course, everybody does. copper. Okay, that's a 3D9 one, but it's in the fourth row, so row 1, row 2. You've had to do this so much that you're never going to forget it. Strontium. Boy, this row is a 5s2 one, so go all the way to row 5. Just stare at your periodic table. 5s2. Yeah, I am 5s2. That's it. Finally, gallium. That is 4p1. So go through the first 3 rows. 3s2, 3p6. I'm in the 4th row. And I'm 4p1. There we go. Okay, you guys were good at this, by the way. 26. What do we do again? We write down the terminal electron of 26. I'm looking at that in the periodic table right now. 1, 2, 3, 4, 5, 6. I got it as 3d6. Electron number 86 is, make sure I see this right, is actually 6p6. And number electron 31, same as gallium. That was real good. So that's 4p1. Go figure. Okay, so first 2 quantum numbers. 3, and of course that's the first quantum number. That's just whatever shell you're in as the last subshell. And your D, S is 0, P is 1, D is 2. Now let's write out the orbits. -2, -1, 0, 1, and 2. Draw your box, your 5 boxes, because you have 5 numbers here. And now let's start filling in 6 electrons. Remember, up arrows first and left orbits first, followed by right. I put in the first 5 to fill in single, and I'm going to double fill. My 6th electron landed in -2, and it's pointed down, so it's -1/2. 6p6, P is a 1, so I got orbits 0, -1, 0, and +1. I got 6 of these though, so 1, 2, 3 are up, next 3 are down, and I'm the last electron, this one. So I am 6, I'm 1, I'm +1, and I'm -1/2. Finally, 4p1 is 4 and 1. My p's are the same as before as what I just put up there, but I'm only going to put in 1 electron. So I'm in the -1 orbital, and I'm pointed up. Very good. Noble gas, sulfur. The row ending before sulfur is row 2, and it's neon. So neon. Now, I'm in row 3. I have to start at the beginning of row 3. So that's 3s2, 3p4. Let's look at tin next. Tin, let me find it. There it is. It's in row 5. So I'm going to go at the end of row 4. End of row 4 is krypton. Now I'm going to start at the beginning of row 5. So that's 5s2. 4d10, and then tin I see is a 5p2 electron. Okay, you can do this. Don't panic. One thing you could do is just by looking at the periodic table, just write out what you know. 1s2, 2s2, 2p6. Then the next row is the sp row. Looks like the highest one I have to go to is 5p, so I'll write out what I see in the periodic table. 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. So let's figure this out. So we got a 1s, so I'll put 1s first. Do I have a 2s2? Yes, I do. I'll put 2s second. Do I have a 2p's anywhere? Yes, I do. Okay. Okay, do I have a 3s? Yep. So I did this by thinking about my periodic table. I looked at the periodic table above in our classroom. I go across the rows and I spit off what they are because I use this to do the electron configuration. I just start listing off what I would do if I was going all the way through row 5. So I looked at it and said, looks like 5p is the last one. So after 3s, do I have a 3p? It looks like I skipped that one. Okay, how about a 4s? I do. So let's cross off 4s. Do I have a 3d anywhere? Yes, I do. Okay. Do I have, so I just did 3d. Do I have a 4p? No. Do I have a 5s? Yes. Do I have a 4d10? Yes. And then 5p. All right. Terminal electrons. Who would have this? Look at row 3 and the second one in. Magnesium. 4d10. Careful, that's in row 5, by the way. Go at the end of the D block, which is column 12, and that's cadmium. There we go. 4d2. Remember, that's in row 5 again. That's zirconium. Just go to the second column of the D block and look at row number 5. Remember, your D blocks are one less. Did this on your quiz well. This is principal. You can just put 1. This would be number 2. This is number 4. Which electron it is always that. Shapes of the orbitals, that's angular momentum. Orientation of orbits, remember it's the orbits themselves. 3. Which ones can be negative? Oh, that's a good one. Well, first one is 1, 2, 3, 4, 5, 6, 7. L is 0 up to 1, so that's negative. Plus or minus 1/2 is, and so is the orbit. So it's number 3 and 4 actually. Average distance is actually number 1, and this is number 4. So hopefully you found that the quizzes, except for de Broglie, which we didn't have a quiz on, covered a lot of this stuff actually. So a couple notes. Know the terms for your things so that when you get questions about how many orbits are in this subshell or what subshells can be this, you can relate it to your quantum numbers. You say subshell, that's quantum number 2, blah, blah, blah. Study your de Broglie wavelength ones since we didn't do a lot of those. So there's a lot of conversions with that and memorize that equation. Practice your Rydberg a little bit because of the math is weird. Also practice your math with the wavelength frequency and stuff and know those equations really well. Otherwise, I'm out. So good luck.